Hello and welcome to the course Remote Sensing Image Analysis and Interpretation, and today I will give the first lecture in this course, which is about an introduction to remote sensing. So we will talk about what is remote sensing and why do we need it and where it can help us in our daily life. So first of all, I want to give you a definition what remote sensing is. Remote sensing is nothing else than observing an object from a distance without physical contact. So mostly when we talk about remote sensing, we talk about satellite remote sensing. That means a satellite is actively or passively observing the Earth with different sensor technologies. But remote sensing can also go down to very close range applications. And it always depends what you want to do and which application you want to solve. So as I said, mostly we talk about satellite remote sensing. That means satellites observe the Earth from space and help people to study large areas. That means the Earth's surface, but also their changes over time. Especially changes are very important. You can think of coastal areas that are changing, like, for example, the coast of Dubai, or cities that are growing very rapidly, like Las Vegas, or glaciers that are melting. And these melting glaciers are an important information for us, for example, when we deal with climate change science. So before I talk about recent developments and remote sensing in general, I want to briefly show you how remote sensing began and how it has grown into its own discipline. And here on the left, you can see the oldest surviving aerial photograph, which is from 1860. And the first aerial photos were taken before the age of planes and drones. And they were taken from hot air balloons. And this is actually such a photo which was taken from a hot air balloon. But also pigeons were used to take photos from the air. And here you can see a picture on the right side. And this is the so-called Bavarian pigeon corps. And pigeons were already used during this time for military applications. So why not using them also for aerial photography? And the advantage was that balloons were easy to shoot down, but pigeons were not. So they took small cameras and they mounted them to these pigeons, and they were attached to these birds, and the timer was set to take pictures every few seconds. And about 50 years later, the era of satellites began. And Sputnik was the first human-made satellite placed in orbit. I'm sure you already heard about it, but I'm always impressed how early this satellite era started. And this Sputnik satellite was launched by the Soviet Union, and it has the size of such a beach ball. It was 58 centimeters. And so it was not very big, but still it was very important for humanity. A very important step for remote sensing was taken in 1972. And 1972 was when the first Landsat satellite was launched. Landsat is the longest running Earth observation satellite program, and it's still active today. And currently Landsat 7 and Landsat 8 are active, and Landsat 9 is scheduled for mid-2021. And during this time, remote sensing became an own discipline. So that was the important things you should know about the history of remote sensing. But now you might ask, that's all interesting, but why do we need exactly remote sensing and how can it help us? The overall goal of remote sensing is monitoring. That means remote sensing offers efficient, cheap, and continuous observation of the Earth and its changes. So we have the ability, the possibility to monitor the Earth and its changes. But now we have all this data, and we need methods which can analyze and interpret in a fast, comprehensive, automatic, and objective way. And for this, we can use machine learning. And in this course, we talk especially about image analysis and interpretation, and also there we can do a lot of things. We can accomplish and solve a lot of tasks with machine learning. And this brings me to the point what you will exactly learn in this course. Imagine you have a lot of satellite images, for example, such a kind of satellite image as illustrated here. And in order to be able to analyze all these images we have, that means to recognize automatically where fields are, where buildings are, we need the help of computers. Because we need the information as often as possible, and also for the whole Earth, not only for specific parts. And it would be far too expensive, far too time consuming, and also far too subjective if all this were done by us alone. And now you could ask yourself, okay, we have computers, so what is so difficult about it? The challenge is that computers only see numbers. So the computers only see numbers, and so you have one number per pixel in this case, which is exactly an information that the sensor has recorded. But these numbers are meaningless at first, because taking pictures is not equal to understanding and seeing what is actually in the image. And so to get closer to this goal that we can get information from images and from data which is useful for us, the computer needs to understand something, and you can teach computers. You can teach them to learn. So what you do is you show the computer a few pictures of a certain land cover, let's say forest, so it can learn a model, and this model can describe what forest looks like. So the computer can learn that forest is green and it has some irregular structure. But what the computer actually learns and sees are numbers. But for us, they are reasonable description of what the forest is. And now, when the computer sees a new image, and in the image there's something green and something structured, the computer knows that this is a forest. But now it's not that easy. Now the computer hasn't seen so far that there are also seasonal changes. So forest is not always green. So forest can be quite colorful in fall, as right now. And there are places also where there are trees, but it's not a forest, such as in a park. So you see, it's not so easy actually to recognize objects, or to identify specific land cover classes in images. But these are all things we will deal with in this course. So I mentioned already machine learning, and machine learning is a set of tools and a set of methods which can help us to analyze and interpret images. And in machine learning, we have two major tasks. So one task is regression, and the other one is classification. Of course, there are also more specific ones, but these are the two major ones. When we talk about regression, we talk about an estimation of continuous characteristics such as yield or building energy needs. So it's the output when you do some regression task is not a discrete number or a discrete class. It's a continuous characteristic you want to estimate. And in contrary to this, classification is when you estimate discrete semantic information such as a land use and land cover. And in this course, we will mostly talk about classification, but the basic principles behind classification and regression are very, very similar. So at the end of the course, when you heard something about classification, you will see that you can also apply this to the area of regression tasks. Okay, so that was the first part with the motivation, and I hope you, you have seen that what remote sensing is and why do we need it and how it can help us. In the next part of the lecture, I want to focus on the taxonomy. So remote sensing is a lot about different characteristics of sensors and how we can actually sense our world. And when we have a look at all these kind of images, I show you here some satellite image, some close range images, and when we have a look at all these images, we can ask ourselves a few questions. So the first question would be, how far away was the data acquired? You see here an image which was taken in the old town in Bonn, but you also see a satellite image from Zeeland in the Netherlands, and in the middle an image about a large city. And so this question is all about the scale. And the next question you could ask is, in which way was the data acquired? And also an interesting question or an important question is, what are the characteristics of the data? And this is when we need to talk about resolution. And I will go through these 3 steps in the next part of the lectures, and I will explain how we can characterize our data and the sensors based on these terms. So, and I will start with the scale. So when we have a look at the scale, I already mentioned at the early beginning, remote sensing is not only about satellite remote sensing. You have also close range applications and also something in between. And so let's start with the close range sensors. The most famous close range sensors is your smartphone. But also a consumer camera, and you can take pictures. These pictures are red, green, blue, and you have it everywhere, and you do a lot of remote sensing when you think about it. But there are also other kind of sensors, for example, in the area of agriculture, which is used in the field to sense some characteristics of about the plants. But we can also use laser scanners. So laser scanners are used to get an 3D point cloud of the environment, and it's a different kind of sensor technology. Then you have satellites. So this is the other extreme. So satellites, you have a lot of different satellites. It's not only that these satellites can monitor the Earth, it's also that they can look the other way around and have a look at other planets, or also the universe or some stars, whatever is interesting for us and what we want to sense. And in the middle, so between these close range application and satellite applications, you have airborne sensors which can be manned or unmanned. And these unmanned aerial vehicles, short UAVs, are got quite famous recently. And I'm sure you already have seen people with some small UAVs, because you can buy them and use them for yourself. But these aerial sensors are used quite often in remote sensing, but also these UAVs, they're used, for example, in agriculture, or when you have disasters, because this drone can fly over specific regions where it would be too difficult to go to, and you can get a good impression about what is going on in the specific area. Okay, so this is about scale. So even if we talk a lot about satellite remote sensing, there are also a lot other sensors which can be used for remote sensing. And in the end, it only matters that you are not allowed to touch it, and when you do not touch it, it's remote sensing. So here you can see, for example, an aerial image of Bonn, which was taken in 1986, and this is there are huge archives where these area photographs are collected, and it's quite interesting to have a look how cities have changed over time. And you can see here it's not a color image, it's not RGB, it's a black and white image, but still. And this is an area image from Bonn, which was taken in 2019. I took it from Google Maps. We all know Google Maps. It's really helpful when you are in a city and you do not know where to go. And so you can see when you compare these two images, especially around the main station, a lot has changed within the last few years. And the quality is quite good, so it's quite helpful. And here you can see a satellite image of Bonn. And the first thing you see is that you cannot see so many details, but the area, the field of view, is much larger. And this is a satellite image taken from the Landsat satellite, and Landsat satellite has a flight altitude of about 700 kilometers. I will talk a lot more about Landsat today in the lecture, and also in the next lectures. So let's come back to our images, and we already talked now about the scale, and now the next question was, in which way was the data acquired? So how did the acquisition process, how has the acquisition process been done? And in the last part, I want to talk about the resolution, and the next part would be the acquisition. So let's have a look at the acquisition. You can classify sensors into active and passive sensors, and this is a good example is shown here for satellites. So when we talk about active sensing satellites, that means active sensors sense transmitted and reflected electromagnetic energy. That means the satellite is actually doing something. So it's sending out the signal, and then it's reflected on the ground, and then it sends the reflected signal. The advantage of such active sensors is that these sensors can or images or data can be captured by day and night, which is quite important. And a good example for such satellites or such sensors are radar sensors or LiDAR sensors. And on the other side are passive sensors. So passive sensors is that you sense the natural energy. That means the energy which is there. And this natural energy is reflected or emitted from the scene, and this is actually what you sense and what you record with the sensor. These data you acquire is more intuitive, so it's more how we sense the world. And also passive sensors are for many tasks superior, so it's easier to work with them, and you get better results. It's not the case for all applications, for all tasks in remote sensing, but for a lot of them. The best example are optical sensors. So when you use your smartphone and you take a picture, This is a passive sensor. When you compare these two sensors, as I said, for the active sensor, you can use it by night. This would not make sense for a passive sensor, because when it's night, there's nothing, not a lot which is reflected, so you would get a black image, for example. So we are used to optical images. That means red, green, blue images. And when you see here, for example, a radar image, you immediately see it's not an image we are used to deal with. So it's not that intuitive, but radar images give us important information about our environment. So radar images capture the structure of the Earth's surface, and you can see here, this is an image of Klein-Altendorf, which is an area close to Bonn, and this you can see a lot of agriculture fields, and the color or the pattern of black and white in this image indicates how rough the surface is. If you see a quite dark area, it means that the surface is quite flat and smooth. If you see a very noisy area, it means there's a lot of structure, for example, like a crop field. And as I said before, you can classify the sensors into active and passive sensors, but you can also classify imaging and non-imaging sensors. So imaging sensors produce an image of the field of view. So the field of view is actually what your sensor can see. And in this area, you get an image. That means you have single informations, and these single informations have a spatial relationship with each other. So in an image, you have intensities, and these intensities are captured in pixels. And so because it's a grid of all these intensities, you can say something about the neighbors, because you have a spatial relationship of all these pixels. The best example for this is a CCD camera. That means the CCD chip in the camera gets this information with spatial relationships between all these pixels. In contrast to this, there are non-imaging sensors. Non-imaging sensors produce one signal for the whole field of view. So it's not that you get single informations and you know something about the coordinates or some spatial information. It's just that you get one information of the whole field of view. It's mostly a small area. So here you can see a field spectrometer. So you go into the field and then you take a measurement in a small area, for example, on a leaf. And then you get one information about it. And it's also called sometimes point measurements, because it's a very small area. Okay, let's come back to our images. And we had already a look at the scale. We had already a look at acquisition. And now let's talk about the resolution. And this is a quite important and also interesting topic, because depending on the resolution, you are able to solve different tasks. And you really need to think before you want to solve your task, which sensors you need, and also how the specific sensor is used for your application. So there are different kind of resolutions, the spatial resolution, temporal, spectral, and radiometric. In short, spatial resolution is the size of the pixel on the ground. It's also known as ground sample distance, so in short, it's GSD. There's a temporal resolution. This is nothing else than the repetition rate of a satellite or some sensor platform, and it means the time interval between two overflights of the same area. Then we have a spectral resolution. This is the number and the width of a spectral band. For example, when you have optical images from your smartphone or a camera, you have a red, green and blue band, and this is acquired from the sensor. But you will see in remote sensing there's a lot more, and you can do a lot more with the whole range of sensors. And there's a radiometric resolution, that means the sensitivity and the quantization of the sensor. And I will go through them and will show a few more details about it. So let's start with the spatial resolution. And what you can see here, so this is an image, and I simulated in this image a spatial resolution of 500 times 500 meters. And this is actually a typical resolution for satellite sensors. And on the left side, I show you a larger part of the image, and on the right side, I show you a little bit more detail. And at the moment, I guess you can see nothing, and or not really. You can see a few colors, but not that you can see any details or identify what is actually illustrated in the image. So this is a resolution of 50 meters times 50 meters. I already talked about Landsat satellites, and Landsat satellites have a resolution between 10 meters and 30 meters. So this is roughly something everybody can download for free. And but you see, you cannot identify single buildings or persons or cars. So no worries that everybody could download a photo where you could be seen in the image. So 50 times 50 meters, I hope you agree that it's okay, but still you cannot see any details in the image. But if you go down to 10 times 10 meters, it looks quite good. And now you can identify, this is the Central Park in New York. The bigger image on the left looks quite good, but if you zoom in and if you have a look at the detail on, I give an example on the right side, you will see that still it gives not a lot of details. But if you go down to 5 times 5 meters, it's okay. You can start to see little boats on the lake. But if you go down to 1 meter or 2 meters, and also to 1 meter, then you can identify a lot of details. And around a few meters, there are a lot of commercial satellites, so we are able to capture such kind of images from space, but you need to pay for it. So after talking about the spatial resolution, I want to talk a bit more about the temporal resolution. So temporal resolution is the repetition rate of a satellite or any other sensor platform. And we generally talk about a high resolution if the repetition rate is less than 24 hours, and we talk about a low resolution when the repetition rate is larger than 14 days. And most of the satellites have a repetition rate somewhere between these two values. And for now, I want to focus on a specific satellite, the IKONOS satellite. And IKONOS satellite is a sun-synchronous satellite. That means its orbit is based on the sun. And it's also because IKONOS is carrying optical sensors, and in order to actually capture something and to get good optical images, it needs sunlight. And in the right figure, you can see a projected map of the world and the projected tracks of the satellite. And similar colors indicate on which orbits the satellite is close in time. So it's not that neighboring tracks are actually recorded one after another. It's more like you have a regular pattern. And that means there can be quite a time that neighboring tracks are actually recorded. And so it takes a while that the whole Earth you get an image of the whole Earth. But there's a trick how you can increase the temporal resolution. So the sensor on the right side, you can see an illustration that the sensor can actually be tilted. So it's not that the sensor is fixed on the platform, it can be tilted by a certain angle, and this angle is the elevation angle. And in this way, the field of view gets much larger and specific areas can seen with a much higher repetition rate. So it's not only that the sensor is only looking down. When it can be tilted, it can also look to the left and to the right. So you have, when you think of the tracks of the last slide, it's not only then you can capture actually images from your regular track. It's also that you can get pictures also from the left and right track. But the disadvantage is that if you tilt the sensor, the spatial resolution will decrease because the number of the pixels stays the same, but the field of view increases. So if you want to increase temporal resolution in this way, your spatial resolution will decrease. And this is illustrated in the left plot. So what you can see here is the average revisit time in days. I again refer to the Econos satellite. And so you have the average revisit time, and on the x-axis you have the target latitude in degree. So 0 means it's the equator, and 90 means it's the pole. And you see 3 different curves, and one curve is assigned to one elevation angle. So the upper curve has an elevation angle of 75 degrees. The middle curve is for 60 degrees, and the other curve is 45 degrees. And you can see the more the angle is, or the sensor is tilted, the ground sample distance, it means the spatial resolution, increases, but the average revisit time increases. Sorry. So there are some tricks, but you need to think about what you want to have and what you need for your application. And sometimes it's much more important that you have a high repetition rate, and sometimes it's that you need more a high spatial resolution. So after talking about the temporal resolution and the spatial resolution, there's the radiometric resolution, which is also very important. And here we talk about how many intensities are actually in an image. So when we have 1 bit, it's just black and white. So illustrated here is one example for a 1-bit image. So you can only find 2 intensities in this image. It can be black and white, it can be also other colors, but the most important thing, only 2 different intensity values. When we have 2-bit, we have 4 different intensities, so 4 different colors in this image. When we have 3-bit, you have 8. With 8-bit, you have 256, and so on. So many satellite images have a radiometric resolution of 16-bit or even 32 bits. So it has a high radiometric resolution, generally more than you can find in images from consumer cameras. There's a relationship between the number of intensities and the number of bits. So you can calculate the number of intensities by 2 to the power of bit. So 2 to the power of 1, when you have 1 bit, is 2. When you have 2 bit, you have 2 to the power of 2 intensities, so 4. And for 3 bit, it's 8, so it's 2 to the power of 3, and so on. So it's quite easy to convert from a bit number to the number of intensities you can find in an image. So after talking about the spatial resolution, the temporal resolution, and the radiometric resolution, I want to talk about the last kind of resolution, which is the spectral resolution. And when we talk about spectral resolution, we need to talk about electromagnetic energy. Electromagnetic energy is energy that is reflected or emitted from objects. And these objects can be, for example, the sun or the Earth's surface. And this energy is carried by waves. And these waves cover a broad spectrum, which is called the electromagnetic spectrum. I'm sure you already heard about it somewhere. And the interesting thing is that remote sensing instruments use the full spectrum of this electromagnetic spectrum to study the Earth. So we can only work and see with in a small range of this spectrum, but remote sensing instruments can see much more than we with our eyes. And this makes remote sensing so powerful and so interesting. So illustrated here is a nice figure which summarizes the full range of the electromagnetic spectrum. Illustrated here are different wavelengths ranging from radio waves to gamma waves. And a small part in this spectrum is the visible light. And this is the part we can see. And when you compare it to the whole spectrum, you see it's unfortunately only a small part. So our sun is a source of energy, and it uses our sun is a source of energy across the full spectrum, and that means it emits all kind of radiation and all kind of these waves. But fortunately, the Earth's atmosphere protects us from the exposure to the harmful waves. And you can see which parts do not go through the atmosphere. You can see this at light blue areas in this figure. And so when we use our smartphone or consumer camera, we can only work with the visible light. But when you take all these remote sensing instruments into consideration, we can work with the whole spectrum. And I want to show you some of these. So, for example, let's have a look at optical sensors. When we have optical sensors, they can have a different spectral resolution. When we talk about panchromatic sensors, this is a single very wide band, mostly in the visible range. So you take the information from the whole visible area and you get one intensity back. When we talk about multispectral sensors, the sensor is able to capture information from several bands with a low bandwidth, mostly in the range between 400 nanometers to 1400 nanometers, which is the range of the visible light, and a little bit more to in the near infrared and also the short infrared range. Then we have hyperspectral sensors, and hyperspectral sensors are similar to multispectral sensors, but they do not have only a few bands. They can have hundreds of bands. And so they are able to approximate the continuous spectrum with many bands and very low bandwidth. And so one band is actually yeah, around 1 nanometer. So this is a very specific information you can get. So let me give you an example that you can understand what I mean when I talk about bands and the bandwidth and what is actually captured in specific ranges. And I want to give you one example. We already talked about Landsat, and Landsat is the longest running Earth observation satellite program. And so Landsat 7 has one instrument on board, which is the Enhanced Thematic Mapper Plus. And Landsat 8 has 2 sensors on board, which are the operational land imager and the thermal infrared sensor. And you can see in this plot a part of the whole electromagnetic spectrum. And these colored boxes indicate which wavelengths and in which range the instruments record and acquire some information. The top row is for Landsat 8 and the bottom row is for Landsat 7. And what you can see is you have the area of the visible light from 400 nanometers to 700 nanometers, and both Landsat 7 and Landsat 8 get some, a lot of information in the visible spectrum, but also in the near infrared, which is from 700 nanometers to 1100 nanometers. Also in the shortwave infrared, which is from 1100 to 3000 nanometers. And also they capture information from the thermal and the long wave infrared. And so some specific of some what would be interesting to add here is you can see the band 8, which is very broad. This is actually the panchromatic channel. So you have an intensity, so one value, one information you get from the whole range. Then Landsat 8 has an additional cirrus band, which is good for the detection of clouds, and it has a coastal band, which is useful for imaging shallow water and tracking fine atmospheric particles like dust and smoke. So the coastal band is the band 1 and the cirrus band is band 9. Yep. So these are multispectral sensors, and as I said already, hyperspectral sensors are similar to multispectral sensors, but they have a lot more information because they capture information from a lot of bands, and also all these bands are quite narrow, roughly about 1 nanometer. And hyperspectral sensors are quite useful when we work, for example, with plants. So when you observe with a hyperspectral sensor, you will obtain a so-called hyperspectral signature for each material. And this hyperspectral signature is very specific for materials. So the hyperspectral signature here is very typical for plants. On the left side, what you can see is a so-called data cube. A data cube is that you have an image in X and Y direction, but also you have a lot of spectral bands. So in the end, if you illustrate it, you get such a cube. And if you have a look now at a specific pixel in the cube, you get exactly such a hyperspectral signature. And if you have a more detailed look at it, you can see that, for example, the reflection in the visible green area is quite high. That's why plants appear green to us. And also plants normally reflect a lot in the near infrared if they are healthy. So what you can see here, where you have high reflectance, this is the near infrared area from the electromagnetic spectrum. And using all these multispectral and hyperspectral channels, you can create pseudo-color images. So on the left is an image which we are used to. You have an RGB image, and so red is 640 nanometers, green is 450 nanometers, and blue is 450 nanometers. When you plot this, you have an RGB image, and this is the typical illustration we are used to. But what you can do is you can just use information from another part of electromagnetic spectrum, for example, the near infrared. And when you now plot near infrared in the red channel, red in the green channel, and green in the blue channel, you get such a pseudo-color image. So it's just that you change the illustration, and you interchange the red, green, blue with other information you want to show. And because plants reflect a lot in the near infrared, and near infrared is illustrated in the red channel, plants appear red to us in this image. So you can actually play around a bit. You will come up with nice images when you play with it a little bit. Okay, so let me conclude. So what did you learn today? Today I told you what is remote sensing, and now you know it's not only satellite remote sensing. We also talk about remote sensing when we have close range application. The only thing is you're not allowed to touch it, because then it's not remote sensing anymore. Now you know why it is useful. Remember what I said, it's satellite helps us to monitor the whole Earth. And it's the only thing what is left is, when you have all the data, you also need to analyze this, and this is what we talk about in the next lectures. We also talked about the taxonomy. So now you know how far is remote sensing, you know what, how often, how exactly you can observe something, and also now you know why some plants appear green to us. Next lecture, I will continue and give you the basics about analysis and interpretation, all what you need to do some classification tasks with remote sensing images in the next lectures. And with this, I thank you very much for your attention, and I hope I will see you again in the next lecture. Thanks.